Hey everyone, thanks for joining our webinar today. My name is Maddie and I'll be kicking off the webinar. I'm joined today by Kent Graziano, the Chief Technical Evangelist here at Snowflake. In today's session, we'll be discussing data modeling. If you have any questions at any time during the webinar, feel free to submit them into the Q&A panel on your screen, and we'll try and answer as many as we can during the live Q&A session at the end. This webinar is being recorded, and we will be sending the recording to everyone within 24 hours of the session. With that said, I'll go ahead and hand it over to you, Kent.
Thanks, Maddie. Good morning, everyone. Good morning, afternoon for those of you who are in other time zones. We're out here in sunny California at Snowflake headquarters bringing you this webinar today, Making Sense of Schema on Read. We're going to walk through how to think about modeling JSON data. As Maddie said, my name is Kent Graziano. I'm the Chief Technical Evangelist with Snowflake Computing. I've been with the company for 3.5 years, and it's been really exciting to be working with this company here in Silicon Valley. My background is I'm actually spent many years in the Oracle world, having started with Oracle and working with Oracle technologies in 1989 with version 5 of Oracle. And with that, I actually did manage to become an Oracle ACE director, and now I'm an alumni of that program. I'm a member of the Oak Table Network, have my own blog called The Data Warrior, which I've been running for quite a few years now. I am a certified Data Vault Master, one of the first in the world, and an active Data Vault 2.0 modeling practitioner. Prior to joining Snowflake, I was a member of the Boulder BI Brain Trust. All of you on this call, I presume, are into data warehousing and business intelligence, so I highly encourage you to go out and look up the Boulder BI Brain Trust. It's a group of independent analysts started by Claudia Imhoff, and they spend their time looking into and reviewing products on the market that are directly related to data warehousing and business intelligence. I've co-authored a number of books and have been very active in user groups around the world for nearly 30 years now, having been the president of the Rocky Mountain Oracle User Group and the Oracle Development Tools User Group. Quick little introduction about Snowflake. We've been around for basically 6.5 years now, with 3 years in stealth, and then coming up on 3.5 years now since we went GA. The company was founded in 2012 by two gentlemen from Oracle who are experts in performance optimization and parallel query execution. Between the two of them, they had over 120 database patents and have filed another 27 patents on the technology that's been developed here at Snowflake. We are a venture-funded company, as I said, based in Silicon Valley, with over $920 million in venture funding from a lot of the leading investors in the area. Our first customers went live on Snowflake back in 2014, with our general availability in 2015. When I joined the company 3.5 years ago, we were only about 100 employees, and at this point in time, we're now at well over 1,100 employees globally, with offices not only in the United States, but all over Europe and in Australia as well. Some fun facts about Snowflake before we get into the seminar. Our max number of queries processed per day in Snowflake to date is over 100 million in a single day. Our largest customer with the largest single table has 68 trillion rows in that database table, and that's, for those of you who are dimensional modelers, it's actually a fact table. So imagine being able to query 68 trillion rows effectively in a fact table. The largest number of tables in a single database within Snowflake is 200,000. And here we are about to talk about data modeling. Some of you may wonder, how could you possibly have 200,000 tables in a single database? Well, when you start loading all of your raw data in and using a data warehouse as a structured data lake, you can easily have 200,000 tables in a large organization with multiple source systems. Our customer with the most data has well over 40 petabytes stored in Snowflake, and they have over 10,000 users accessing that data. Their maximum throughput on any given day so far has been over 3,000 concurrent users at any time accessing Snowflake. The agenda for our webinar, we're going to quickly go through some definitions, establish our basis of conversation here. We're looking at what we mean by schema on read versus schema on write. And we'll have a little chat here about why we still need data modeling. Then for those of you who are not as familiar with this technology as others, we'll talk about exactly what is JSON. And then we're going to go through a couple of detailed examples of JSON documents, and I'm going to show you how I converted those into a third normal form model as well as a data vault model. And then at the end, we will have time to go over some questions. So first off, what do we mean by schema on read? Well, this is a concept that came around here over the last 10 years with the big data movement and the evolution of document stores and other NoSQL databases. The concept was we need to find a way to get data into systems without having to spend a lot of time modeling up front. We were trying to be more agile in our software development world, so we wanted to, get things going quicker and not spend what was typically months, if not years, in an enterprise data modeling effort before we could start building an application. So folks started doing these databases and document stores where we could just create an application and store that data in the back end without having to do all the modeling up front. Many people used to call this unstructured data, but in reality it is semi-structured data, as you'll see. And Claudia Imhoff actually calls it flexible structured data because the structure of the data can change over time. And this is one of the benefits of using a schema on read approach, is to not have to spend time remodeling the database before you could store the data. The idea was to simply be able to load and go, and that allowed us to move into a more agile framework specifically for application development. Now that doesn't mean that it was great for those of us who are doing data warehousing and business intelligence, which is why we're going to look at how we think about this from a modeling perspective, because we really got to understand these structures. Schema on write is what we have been doing for over 30 years in our relational databases. It's tables and columns and views and the things that all of us database professionals are very familiar with. It does require that you define and design the structure in advance before loading data into the system. So that upfront modeling is something that we have to engage in. When we're talking about data warehousing, we've got to be able to map our source data to the database tables. And I'm sure many of you have had this experience of a source system changing on you when you received no change notification whatsoever, and that resulted in your ETL or your ELT process failing because the structure of the inbound data was different and the ETL didn't know what to do with those changes. So this is one of the downsides that was seen from schema on write, which is one of the benefits, though, that folks saw schema on read, is the structure could change and things wouldn't break. Applying that in the data warehousing world, of course, is a little different. But the world has changed on us here over the last 10 years. We now have data coming in from many, many different sources, and the variety of data that is coming has increased dramatically with the advent of mobile and IoT in addition to all of our enterprise apps that we are already getting data from in our ERP systems, and then just general weblogs. IDC recently had an estimate that they're going to have 163 zettabytes of data by 2025. And the big data world has sort of helped us solve the problem of how we're going to store that data, being able to have the cheap storage to do it. The question still remains, though, is what are we going to do with the data? We have to be able to take advantage of that data, and that requires us to understand this data. Which brings me to that conversation of, why do we still need to do data modeling? Who needs to still do data modeling? And the answer that I consistently have to give is we all still need to do it, especially those of us who are in data warehousing and business intelligence. If we're going to take advantage of the data, we have to be able to use it. In order for us to use it for business advantage, we have to be able to understand it. And that in data terms is what we generally refer to as metadata. And part of that metadata is the structure or the model of the data. So even the term schema on read includes the word schema. And schema is just another name for a model. It's generally what we think of as the data model that's within the database, within a particular schema or user in the database. So if we want to query that data for business intelligence, advanced analytics, to be able to use that data for machine learning and artificial intelligence, we've really got to understand the structure, we've got to understand the content of that data. So that means that we have to understand the model. So we still have to do data modeling even if we're in a schema on read environment. To actually make use of that schema on read, we have to understand the model of the data. Very few of the tools that are available today can actually look at a semi-structured document, such as a JSON document or an XML document, and interpret it on the fly. So many people have found that they still need to come up with what we would consider a traditional relational model when looking at this type of data, so that we can potentially expose it at least as a SQL view. So what is JSON? Down to the basics here. When I started working with Snowflake, I honestly really did not understand JSON, wasn't really sure what it is, but over time I found out that the JSON itself is very structured, but it really stands for JavaScript Object Notation. And it was designed to be a readable format for structuring data. So this is the definition of JSON, a minimal readable format for structuring data. So even though we call it semi-structured data and people often call it unstructured data, it really is structured. It's just not structured in the way we were used to in the database world of being tables and columns. This was designed really to supplant XML. As we moved into the web world in the early 2000s, we had web servers and weblogs and many of these things. We found we needed a different way to articulate that structure than XML. XML wasn't doing it for us, so the industry switched over to JSON. And we've discovered there's a lot of that out there. JavaScript itself is a very popular language for people to write applications in. Many REST APIs for IoT and mobile use JavaScript and output JSON. So when we're looking at weblogs, particularly social media, if any of you have ever looked at the feed from Twitter, when you pull data via the Twitter API, that's all coming out as JSON. So if we're trying to do customer sentiment analysis by looking at tweets and looking for particular hashtags, that's all JSON data that we have to figure out how to interpret so that we can join it to our more structured data, perhaps in our CRM systems. The good thing about JSON that I found is it's very self-describing, so it's quite portable, but it's also human readable. so we can start looking at it, and that's kind of the exercise we're going to go through here, is taking a look at those JSON documents and interpreting them in a way that makes sense for a database. There are many data sets available out that are public domain, things like data.gov and datasf.org, which is San Francisco, and then the City of New York has data.cityofnewyork.us that's providing all kinds of data that people may want to use to augment their analysis. With the advent of new technology such as Snowflake, we now have the ability to ingest JSON natively into the data warehouse system without having to pre-parse that data and split it out into tables and columns, but to be able to load it natively and write SQL statements that actually allow us to join that JSON data with structured data. So if we're going to do things like that, then it's incumbent on us to understand even more so how we're going to model it. Many of our Snowflake customers are ingesting trillions of rows of web logs and creating SQL views on top of those to expose the data so that they can join it with relational data from their other traditional systems. So in order to do that, they had to understand how to model that data in order to make views that made sense. So let's now start working our way through an actual example of a JSON document. So this is our first document, which is showing us colors. And the curly brackets on the outside are the delineation for the actual JSON document itself. Within a JSON document, it's really a key value pair structure. So there's a key, which in database terms we would tend to call a column or a column name, and then the value that would be normally stored in a database shows up here after a colon. So you have everything in double quotes. On the left is the key, and then there's colon, and then double quotes, and the values which are on the right, which are applied to those keys. So think in terms of the database terms, the column color and the value stored in that row, if you will, is white. Within a JSON document, you also have the ability to have nested keys, which are delineated again by more curly brackets. So in this example, we have code, and code is made up of two parts, RGBA and hex. We also have the ability to have arrays in a JSON. So that's delineated by square brackets. So in this case, we have RGBA has 0,255, 0, 1 within square brackets, and that indicates an array of values assigned to that particular key. So now let's look at how do we turn this into a third normal form logical data model. First off, we're going to look at color, our key of color. I'm turning this into an entity. So we're doing logical modeling rather than physical modeling. So this is a concept. We have the colors entity with the color name as the attribute. And I'm trying to do agile modeling here, so I'm going with the information I have in this JSON document and have decided that in this case, the color name is my primary unique identifier. The modeling tool that I'm using here is actually Oracle SQL Developer Data Modeler, and this is the logical modeling tool within that data modeler. So the hashtag there in blue to the left of color name indicates that it is a primary unique identifier. The red star indicates that it's a mandatory attribute. Next, we take a look at the next two keys of category and type. And those I am translating into lookup entities. Those are reference entities. So we have category code and type code. And I'm just abstracting this out based on the structure of the JSON document that we are looking at. And next we have our nested key code, which is made up of RGBA and hex. And when I did my research, I looked into it and discovered that RGBA stood for red, green, blue, and alpha. And so I pivoted those out into component parts and turned those into attributes within my reference entity of color code. Now when we go and convert this now from the logical model to a schema model or a database design, it looks like this. So you see the color of the diagram has changed from blue to yellow, and we're now going from entities to tables. So in this case, the colors entity is now a colors table, and with the primary key, that's what the P stands for, a color name, and then category code, type code, and hex, all inherited from the relationships that we saw in the prior diagram. So these are now the foreign keys off to our reference tables. So we have the color category has become a table here with a primary key of category code, and the color code table with the primary key of hex, and red, green, blue, and alpha as other mandatory attributes. Then our third reference table here being color type, again with the type code. So all I've done here is transition from my logical concept of entities to an actual database design that any of you folks should understand. This is the model. So we've now turned this JSON document into tables and columns as a representation in a data model diagram. Now there are many options that we have in how we choose to model things. Since we're talking about data warehousing and business intelligence, you may choose to simply have a denormalized model, in which case all of this is in one single table. So the table I defined here is color, with color name being the primary key, category, type, RGBA code, and hex code as being columns in that table. So effectively all I've done, I've used one table to represent this particular JSON document. So every row within the JSON would be one row in this table as represented here. And this is a design choice based on your use cases and what you're trying to accomplish with that data. So it can be as simple as taking the document and turning it into a single table. Because we were talking about data warehousing, one of the other examples I wanted to give you is what the same document looks like in a different modeling technique. So in this case, we're going to talk about Data Vault. And so Data Vault is a methodology and modeling technique developed specifically for data warehousing design. For those of you who aren't familiar with it, it was invented by a gentleman named Dan Lindstedt, and he published the first papers on it in the early 2000s. And I've been a user of this particular methodology for my data warehouse designs since 2002. So in Data Vault, we have three concepts: hubs, links, and satellites, and we'll show you here in the next couple of slides what that looks like in terms of this particular JSON document. So first off, I have defined hub color category. And so in Data Vault, all hub tables have a primary unique identifier, which is a calculated key. We have the business key, which we would call a natural key in normalized modeling. So in this case, the unique key is, again, category code. And every table in a Data Vault design carries two pieces of metadata with it: the load date and the record source. So we're always tracking when the data was loaded into the warehouse and what the name of the source system was that data came from. So this is our first hub in defining our JSON document in a relational manner. The next hub is hub color type. So again, we have a primary key, we have hub code as the unique identifier, and a load date and a record source. Our third hub is hub color code. Again, with the hex as the unique identifier, which I chose in the logical model we saw a number of slides back, and again, load date and record source. Now, one of the key differences you'll see in Data Vault is the attributes that are related and potentially changeable over time hang off in a structure called satellite. The satellite in this case is hanging off of hub color code, and there you have the red, green, blue, alpha attributes are in this satellite. And the satellites in Data Vault are like a type 2 slowly changing dimension. If you look at the diagram, you can see the primary key not only includes the inherited key from the hub, but the load date that we have in every structure in Data Vault is actually part of the primary key now. So when we detect changes in our inbound data into a Data Vault style warehouse, we load those changes into the satellite. So this is where we're doing our change data capture. And then the relationship between all of these hubs is expressed as a link. And so this is giving us our ultimate definition of colors as defined by this JSON document is really the intersection of a color code, a color category, and a color type. So in the link structure, you'll see a calculated hub key or link key, followed by a number of unique key components, which are the inherited keys from all the hubs. So the link structure is effectively a many-to-many intersection entity, and that's how relationships are recorded in a Data Vault style model. And this allows us to load data into our Data Vault regardless of the cardinality. So over time, often we get cardinality changes and differences across different source systems for what we thought was a static relationship. And the structure in Data Vault gives us the ability to absorb those changes without having to actually change the structure of the data model. And then we can also have satellites off of our links, and in this case, the color name is hanging off in the satellite off of our link. So given we're using schema on read, we have to ask the question, what happens if the JSON structure changes? It is, as I said before, flexibly structured is one of the terms used for JSON type data, flexible structure or semi-structured. So when it changes, which was the point of our schema on read concept, we want to not have to change our structures. So with Snowflake, a number of NoSQL databases, and even in Oracle, if you are using the native functionality within these databases, in Snowflake it happens to be called a variant data type that can natively ingest JSON data, you don't have to change the structure inside of Snowflake. The data will load in and it won't break, which means that your ETL processes isn't going to break if you're loading JSON directly into Snowflake. Other examples of what could possibly happen here, as you saw, this is a fairly minimal document, so color category and color type don't have descriptions. In most cases, when we're all defining and designing schema on write databases with code tables, we almost always have a description. So it's conceivable that over time the JSON document might change. You could get a new attribute like description. In the third normal form model, what that means is that you pretty much have to do an alter table and add the column. In the Data Vault model, you may do the same thing, or you have an option to potentially add a new satellite to the model, which would then allow you to keep loading the data as it was, but express the new structure with a revised model by adding additional tables. Onto a more complex example. As you can see, this document has quite a few more attributes in it and a little bit more data. We still have a nested element example. In this case, we have a phone number, which it has two components, area code and subscriber number. And now we have a new sort of construct from the last document we were looking at, which is a nested array of elements. So we have a children key that has the square brackets, which indicates an array. But then within that array, we have other curly brackets, which indicate nested elements. So children are defined as having name, gender, and age. And in this case, we have an array of 3. So there are 3 children associated within this document. And the next really interesting part is getting a nested array of values within a nested array of elements. So in cities lived, we have again, the square brackets for an array, and then within that, again, are more nested elements within the array of city name and years lived. In years lived itself, again, we see another set of square brackets indicating yet another level of array, where we now have 4 years listed for the years that someone has lived in that particular city. So now we're going to turn this into a model like we did before. So back to our logical model, we now this time have a person entity with a name, age, and gender. Now normally in relational modeling we wouldn't have something like age, we generally have birthday. But the JSON document we're dealing with only gives us the age, so we're going to have to go with that. Not necessarily best practice in normalized modeling, but we're trying to do agile schema on write modeling on top of a schema on read document. So we're going to go with this for this round and say, we're going to have age as an attribute in our person entity. Now our nested elements below person in that document was phone number. So we have a one-to-many relationship modeled here for phone with 2 attributes, area code and subscriber number, and those 2 attributes combined make the unique identifier for that phone number. And next we had our nested array of children. Well, whether or not all parents agree, children are people too. So we have a recursive relationship diagrammed here for the actual parent-child relationship on the person entity, because the attributes for children are exactly the same as the attributes for person, name, gender, and age. And there's an implied relationship within this JSON document that the name at the top of the document, in this case was Johnny Appleseed, these are his children. And next we have a lookup entity or reference entity for city. Given we've only got one attribute, we're going to have to go with the primary unique identifier. In this case is the city name, though we all know in the real world there is a Paris, France and a Paris, Texas. So city name really isn't good as a unique identifier from a traditional perspective. But again, we've got a JSON document here. This is the only information that we've been given. So this is how we're going to have to model it for the time being. Cities lived is an intersection entity between person and city. And the year that the person lived in that city is part of the unique identifier. The modeling method used in Oracle SQL Developer Data Modeler is actually referred to as the Barker methodology. And so this is a little different than what you might see in an Irwin diagram for representing the relationships and the cardinality between the entities. But the crow's feet lines that you see going from person to cities lived and city to cities lived is a one-to-many. And the little line across it just below the 3 little prongs there indicates that the unique identifier from the parent entity is being inherited into and part of the unique identifier for the subordinate entity. So when you look at city lived, the way you interpret this is that the unique identifier for city lived is the primary unique identifier from person, which is name, the primary unique identifier from city, which is city name, and the year as indicated in the diagram. When that translates into a schema model, then you see tables as we saw in our previous example. So we now have a city lived table with name, city name, and year as being the primary unique identifier, primary key in this case, the primary key for person being name, with a foreign key relationship back to itself for parent name, which is an optional relationship because in the recursive hierarchy somewhere there is a top node that won't have a parent. Then primary key is city being city name, and then phone, the primary name being primary key for phone being person's name plus area code plus subscriber name. Now, this model, even though it is a schema on write model, it can absorb a few changes in the potential changes to the JSON schema. If the kids get a phone, well, since they've been defined as persons, then the kids' phone numbers can simply go into the phone table. If the kids move out, which someday, children do move out and get their own place to live, we can record that in city lived. So even though we're dealing with a schema on read flexible schema document, if these kinds of changes happen to those documents, the schema on write model we're using does not have to change. If we get more details on city, like the state and the country, we would need to do an alter table and add additional columns. Likewise, if we get more details specifically on children, we may be adding columns to the person table that would potentially be optional columns for the child subtype, or we might even be adding an additional table into the schema that handles the information that we've been given. So there are some options for you to think about going forward as schemas change. In Snowflake, when this sort of thing happens, even though I'm modeling these things as tables, they get implemented as views. And so if the underlying JSON document changes, we simply create a new view or alter the view, and we have customers, as I said, who've been doing this for up to 3 years in using Snowflake as we sometimes call it a data lakehouse, where they're able to load the semi-structured data directly into tables in Snowflake and then build views on top of them. Now let's take a look at the same data from a data vault perspective. So back to our hubs, links, and satellites, we now have a person hub this time, with the name being the unique identifier. And then the sat person in this case includes all the attributes that are related to person, which include the name, the area code, subscriber number, age, and gender, all end up in our satellite. So over time now, as we get another JSON document that comes in for Johnny Appleseed a year from now, and his age is changed, that age change would be captured and recorded in the satellite. The relationship between children and parents is now incorporated into a link structure within the data vault modeling technique. And this is how we handle all relationships in data vault are handled through links. So this allows us to have that one-to-many and many-to-many relationship between persons. In this case, we're modeling it as children. We have another reference hub for city, and then the city's lived relationship is represented by a link between person and city. So basically the same as it looked in our relational model on the prior page. Within Data Vault, we have a couple of special scenarios, and this happens to be one of them, a transaction link, where part of the key is defined by an attribute rather than a relationship to another hub. In most cases, links, the primary key of a link is defined by the inherited keys from a number of hubs. In this case, year itself does not have a hub because it would be more or less senseless to define a hub that was just a list of years from, we'd have to go to back, 3000 BC to somewhere in the future. So instead of modeling a specific hub to represent that column, we simply put it into the link itself and make it part of the primary key. So if a JSON changes in this case, the schema we have here can absorb a number of changes. So as before, if the kids get a phone, that works out fine because the children information is being recorded in the person hub and the person satellite. The kids move out, same thing. The intersection link of city person and city lived still gives us the ability to record that. The one additional thing we get because of the recursive link structure on person is we can now record two parents for the same kid, which is the normal scenario for most of us. In the prior model we were doing, we actually could only model a one-to-many relationship of one parent to many children. With the data vault model, we can actually now absorb a new set of information from a JSON document and record it without having to change our model. As we extend the model and we get more details on city, we would simply add a satellite table off of hub city to include whatever additional attributes are there. If there's an extensive amount of attributes being added, it's possible we've got new hubs and new links for the model, which again are additive, which allow us to still be very agile in our modeling technique to expand our model over time as we discover new relationships. The bottom line of all of this is that even with the schema on read world, there's still a very important role for data modelers and data architects, particularly in the business intelligence and data warehousing space. As great as the concepts of schema on read are, and the usage of things like JSON documents to store transaction data and to make application develop more agile, we still have to be able to represent this data in a form that makes sense to business users if we're going to use it for analytics to drive value for our business. We have many customers at Snowflake that, with the advent of our technology, are able to now easily integrate JSON web logs, IoT machine data, all of it in this semi-structured format directly into their data warehouse environment and join it to the normal structured data that we've traditionally had in data warehousing. And so they're able to get much more value out of all of this data. And we've all heard for at least the last 10 years since the advent of big data how 80% of a corporation's data is really unstructured. Well, I can tell you after the 3 years of working here with Snowflake that, yeah, 80%, when you start looking at all of the data that a company has access to today, it's at least 80%, but it's not unstructured. It is indeed semi-structured. And we have to be able to interpret that and present it to analysts and data scientists and knowledge workers and even citizen data scientists in a form that they can easily consume. And getting it into a relational view in Snowflake and exposing it with Tableau or Power BI or whatever your BI tool of choice is the way to derive value from this data much more quickly and at a much lower cost. We have to be able to read this data. We have to be able to understand the design of the data, and the best way to do that is still through a traditional relational model, whether you want to use third normal form, you want to use data vault, you want to use star schemas and dimensional models, the choice is really yours on the modeling technique. The point of this particular talk was to get you to think about these things differently, to not be intimidated by things like JSON and Parquet and other semi-structured approaches just because you come from a relational background. There are ways to interpret this and model it so that it's understandable. I gave this seminar a couple of weeks ago over in Australia, and I even had someone who didn't know anything about relational databases but was a graph database expert. And all of these documents can be expressed in a graph model as well. So if you're using something like Neo4j, you have the ability to do this and interpret the data in a graph model, not just a relational model. So just a little plug here. If I was talking a lot about Oracle Data Modeler, I do have an ebook available out on Amazon called Better Data Modeling, and gives you tips and tricks on how to use Oracle's Data Modeler. For those of you who have never heard of Data Vault before, I have an introduction to the Data Vault 2.0 modeling technique, also available as an ebook out on Amazon. And I sure hope that all of you are interested in our data warehouse as a service platform, Snowflake. We have a free self-service account that you can go out and sign up for, where you can get up to $400 worth of credits to use for 30 days to try out the platform, so you can try loading some JSON document directly into Snowflake and building views on top of it. So if you're interested in doing that, you simply go to snowflake.com and look for the free trial button. And with that, I think we're ready to take some questions. Let's see, we have a few questions online. First question I've got here: on the example where a person has children, what if the individual has no children, and in the source JSON structure, the subdocument is only included if not null? Can Snowflake account for this? Excellent question. Yes, in fact we can. So you could have some documents that have the nested children structure in it and others that don't. So indeed, those would be null. And if you build a view in Snowflake, and this is one of the where I like to say Snowflake really makes schema on read a reality. You create a view that incorporates those keys for children, but they're not there in a particular document. They simply return as null in the view. So the view itself will not break, and that's why I said it's a very resilient approach and really does take advantage of the schema on read features. Oracle, another comment here. Oracle supports JSON. Help me understand how different you are with respect to Oracle and Snowflake Advantage without talking about cloud. Well, that's a great way to phrase that question. Yeah, not irrespective of cloud. Snowflake invented a new data type called variant, and the way the variant data type works in Snowflake is as you are loading the JSON data directly into that column, our metadata engine scans the document and catalogs and records all of the keys in our metadata engine. And effectively, we're creating micro columns in metadata. So when you query a JSON in Snowflake, it's looking in the metadata, finding the keys referenced in the SQL statement, and we have pointers that allow it then to go directly to that point in the JSON document. So our performance is nearly the same as if you had broken it out. Our customers report to us that it's within milliseconds. If they go and were to take the JSON document and split it into tables and columns with ETL and then query it, the response is nearly identical to going directly against the JSON. where my understanding of the Oracle technology is we're using what used to be known as the Oracle context option, and it requires some specific indexing while the performance may still be good. The question I don't know personally is how well Oracle's technology scales to the billions of rows of JSON and trying to query and aggregate across that, where I do know that Snowflake customers have often billions of rows, and one customer I know, it's trillions of rows of data with JSON in it, where they are doing regular queries against it by simply putting views on top. I'm just looking through some of the other questions that we have here. On the example where a person has children, what if the individual has no children? Okay, we already did that one. Is the JSON view approach in Snowflake as performant as doing the data modeling up front? I basically just answered that question, Christian. It's within milliseconds. So if you were to do all the ETL and split it out, it will definitely be faster, but now it becomes a question from an agile perspective of how fast is fast enough. Building the views is obviously much quicker than writing, speccing, and QAing the ETL code to break it all out. We have customers who were doing processes prior to coming to Snowflake where they were doing this type of work and they were splitting everything out manually via ETL and then loading it into relational tables. One of our customers, that process took upwards of 24 hours to get their event data into a relational database so they could query it. When they moved over to Snowflake, that entire process shrank to 15 minutes. So their time to value was radically improved because they eliminated an up to 24-hour data pipeline to get the data accessible in a relational format to simply loading it into a variant in Snowflake and putting a view on it. And so they were very happy with that, and their performance was, as I said, within milliseconds because of the fact that we do this micro columns approach within our metadata to make the access even faster. Another question here, if JSON can be imported directly in Snowflake and work on views, where is the question of data model and data modelers? Well, somebody still has to design those views. So that still requires a data modeler. I mean, to me, a view is part of the data model, right? It's the model that we are exposing to folks who are going to query the data. And I've been doing this for nearly 30 years, and my reporting views are often different than the underlying physical structure in the database. And so this is just another extension of that. We still need to have somebody model that data and translate it into something that is usable. Another question, from Christian again. I mentioned Oracle Data Modeler. How do you recommend people manage views on Snowflake? I always have and always will recommend people use a data modeling tool of some sort. Oracle Data Modeler happens to be my tool of choice because I'll say grew up using Oracle Case, then Oracle Designer and Oracle Data Modeler, and Oracle Data Modeler does indeed connect to Snowflake. I've got a blog post out on my Data Warrior site that talks about how to use our JDBC connector to connect Data Modeler to Snowflake. You can use ER Studio. A gentleman in Austin's written a LinkedIn post on how to connect ER Studio. I've heard people say they've been able to connect Irwin as well. We're currently working with Irwin Product Management to get a native connector to Snowflake. So my recommendation is always use a data modeling tool of some sort so that your views are documented and you can expose them through a data model diagram to your report writers, rather than you can have, of course, have a data dictionary. There's all kinds of things you can do, but I've found in my experience that having a printed data model diagram is a great way of communicating the structures specifically to people who are writing reports against those structures. Does Snowflake read all the documents from a particular collection to define the data model? I don't think we do in the way that you may be thinking. When you query the JSON in Snowflake, which our next webinar is going to go into details on how you do that, you do have to look at the structure. We don't automatically infer the model and turn it into views. That's why I've gone through this data modeling exercise. So another question here from Nikhil. So what I understand is we need a data dictionary on top of the JSON to query the data. So how does this help making quick changes in the Agile methodology? Well, what it does, yes, if the inbound JSON structure changes, you still have to discover those changes somehow, whether it's through a change control process or through periodically reviewing the structure. What it does do is it makes your ETL process more resilient. You will not have your data loading process break because the inbound JSON changes. And so that allows us to be more flexible in our approach. And as soon as that changes in there, we can, of course, build a view, which is always way faster than writing a bunch of ETL code. So there's two ways in which this allows us to be more agile. And we're coming up on the end here. Get a couple more questions here. How should we think about dev, test, and deploy views on Snowflake? Well, that's a much more complicated question, but real fast, high level. Many of our customers do have dev, test, and production, if you will, databases within their Snowflake account. So you can do it either by separating things out that way, dev, test, production schemas, or you could even do things like having naming standards on your views. My recommendation generally is to have a dev, test, and production database. All right, Eric asking semi-structured data equals tag data without a schema, so JSON can be structured or semi-structured. Avro is structured. Yes, absolutely true. And it looks like that is all of our questions. Thank you very much, everyone, for attending today. I hope you found this session helpful. And as Maddie said earlier, we'll be making this session available via recording.
That's right. And as a quick reminder, Kent will also be hosting another webinar on May 2nd called How to Model JSON with SQL. That'll be posted to our site later today, and we definitely love
No, that's the one we just did.
Oh, okay. With that said, thanks for joining, and we hope to see you again.